afterward, the talk will be posted on YouTube like we did last year. So hopefully more and more people will revisit this talk, not just for the rest of the year, but also like 10 years afterward. We're going back at this talk and, and figure out what's been said in the early days of the development of Habitable Worlds Observatory. So great. So today we have Marc and Swara going to talk to us about from the Galaxy Growth Working Group of the Habitable Worlds Observatory, talk about all sorts of things regarding the kind of galaxy science that Habitable World will be able to do. So for those of you who are joining us for the first time, we are NASA Cosmic Origins Programs Galaxies Science Interest Group. So we are the part of NASA that sort of bridge to the community and take input from the community and communicate that to NASA to make sure NASA missions will do your science, especially for the big flagship missions and especially 20 years down the road. So Habitable World Observatory, as you will hear more in this hour, it's named that, but really in essence, it is a super Hubble and it's supposed to do all sort of astrophysics. So please get behind the mission, see it as your mission, get involved early on, contribute science cases, and so that we can make sure it will do your science 20 years down the road. All right, so all the talks from the seminar series will be recorded and posted on YouTube afterwards. So if you can make this time, you can always revisit the talks and the slides online. All the talks in the first week of first Wednesday of the month are filled and the schedule is available online. But if you're interested in giving a talk on timely results and things that you want to make public, this is the platform for that as well. So all the third Wednesday of the month are, we call it Fill As We Go. So they're mostly open. If you're interested in giving a talk, please reach out to me. You can reply to that. You can probably see my email in that broadcast email we sent to the Galaxy Science Interest Group email list. So without further ado, let me hand it over to Marc and Swara, and they'll tell us about uncovering the drivers of galaxy growth with uncovering the drivers of galaxy growth working group from the Habitable World Observatory. All right.
Okay. Thank you, Aaron. Good morning, everyone, and thanks for joining. Thanks to Aaron and Bene for inviting us to present the science cases from the Uncovering the Drivers of Galaxy Growth Working Group. So we're talking on behalf of our working group. Next slide. So the Habitable Worlds Observatory is the high priority recommendation from the Astro 2020 Decadal Survey, which recommended a large, no less than 6 meter, ultraviolet optical near-infrared ultra-stable space telescope, with the goal to identify and characterize habitable planets and to provide new insights into the formation and evolution of cosmic structure. So early this year, a number of science working groups and technology working groups were formed to work in a coordinated way to identify key science objectives and also to identify the technologies that need to be advanced for the HWO to do the revolutionary science that we expect from flagship missions. So the science working groups were tasked to develop the science goals, quantify the science objectives, and outline the observatory and instrument capabilities. The technology working group was tasked to study the design and architecture options and also assess the technologies and risks associated with these options. Next slide. So here is a list of the current HWO working groups. So we have 4 science working groups, the Galaxy Growth, which is led by Marc and myself, and the evolution of elements, living worlds, and solar systems in context. And the evolution of elements is another working group which has a lot of synergies with the general astrophysics problems that we deal with. And it's led by Janice Lee from Space Telescope Science Institute and Paul Cohen from NASA Goddard. And all of these working groups actually work in a very coordinated fashion. So next slide. So galaxy growth, as you know, deals with problems associated with galaxy formation and evolution, and it covers a broad range of themes. So we have subgroups within the galaxy growth working group that deal with or that look into science cases in specific topics within this big umbrella of galaxy growth. So we have AGN over cosmic time, which is co-chaired by Vivian from the University of California, Irvine, and Chris from University of Texas, San Antonio. We have the IGM and the CGM working group, which is led by Sanj and Joe. Sanj from University of Arizona State University and Joe from New Mexico State University. We have the ionizing photons and their history subgroup, which is led by Stephen McCandless from Johns Hopkins and Alison Strom from Northwestern University. And we have the dark sector, which is led by Jason Rhodes from JPL in Pasadena and Richard Massey from UK. So as you can see, our co-chairs are from different universities across the country, and also we have international collaboration. Next slide. So what we were tasked, so the main task of the Galaxy Growth Working Group is to identify key science observations that will tell us about the physical processes that actually drive galaxy growth. Now, this involves a variety of topics: the role of the environment, how gas flows in and out of galaxies, the entire cosmic ecosystem around galaxies, how supermassive black holes form, how they grow, and how their growth is linked to the growth of their host galaxies, understanding the production of ionizing radiation and what is the history of the ionizing sources and the galaxies that produce them, and also exploring the impacts of dark matter and dark energy on the large-scale structure. Next slide. So the working group activities actually started early this calendar year, and our first year deliverables are science case development documents that are completed, which document the key science objectives and the physical parameters that we want to measure and the kind of observations that we want to do, and also document the precursor science that needs to be done in preparation for HWO, and document the sources from where the targets can be selected for from the upcoming planned missions like UVEX and Roman. And there are science tools that are available to develop these science case documents, and that includes the exposure time calculator and the simulation codes that are available from the simulation working groups. And our timeline is to produce at least one driving science case that is completed by each subgroup by the next HWO face-to-face meeting, which is happening in October. And we hope to complete all of the science cases by the end of the calendar year. And the outcome of these working group activities is essentially you have a good idea of the kind of sensitivities that you need to reach to do this, to make the science possible. So like the spectroscopic sensitivities, what are the short wavelength cutoff, the field of view, and imaging depth, all of which has a role or informs the design and architecture of the observatory. And we have some initial assessment of the key instrument parameters and also the observatory parameters. So in the next slides, we want to discuss the science cases that we are working on right now, and I'll hand it over to Mark to talk about the first two science cases.
Thank you, Swara, and pleasure to be here this morning or afternoon, depending on where you are. We're going to talk about one science case in each of those four areas that Swara highlighted. I'm going to start off with one of the science cases from the dark sector sub-working group to reveal the nature of dark matter from small-scale gravitational lensing. And this is a science case that is being led by Qihan He, Matilda Josic, Russell Smith, Richard Massey, Tansu Delan, David Lagututa, and Jason Rhodes, all of whom have made key contributions to the science case you will see here. So what is the goal of this particular case? And this is a very broad one, is to understand the nature and composition of dark matter and its impact on the evolution of our universe. And many of you may know that dark matter comes in different temperature regimes depending on how relativistic the particles that make up the dark matter are. Briefly, it's kind of like the Goldilocks story. It's either hot, warm, or cold. And pretty much we've ruled out the idea of a universe dominated by hot dark matter. There simply would not be enough. There's too much small scale structure in the universe to be compatible with a hot dark matter dominated universe. So we know that hot dark matter is likely not a dominant particle in the cosmos. Cold dark matter, on the other hand, does very nicely in explaining the structure we see. But warm dark matter also has a role that it might play, especially on small scale scale lengths. And so one of the goals of this science case with Habitable Worlds is to see if we can constrain the properties of dark matter, especially at small scales. And the way this will be done is to use strong gravitational lensing. Many of you know that this was a prediction of Einstein's theory of general relativity, that if you have a mass in the foreground, it can magnify objects in the background and reveal the presence of matter, all the matter, in fact, in between the source and the observer. And so here's a really nice example that was part of a Galaxy lensing survey by Vighetti et al. In 2010. And here you see a case of a foreground lens galaxy, which they've labeled G1. And it is aligned with a very blue background galaxy, almost a perfect alignment, resulting in what we call an Einstein ring, or almost a complete ring, where that galaxy's image is stretched almost in a complete circular pattern. But one of the neat things about this particular example is you see that there's a second galaxy, G4, acting as a secondary lens, and is sort of perturbing the lensed image due to G1. And from that secondary galaxy, you can learn the distortions of that secondary galaxy tell you a lot about the mass properties of the dark matter halo around that secondary galaxy. And so this allows us to really potentially characterize the properties of very low mass galaxies in the universe. And that's the sort of core idea behind this science case for Habitable Worlds Observatory. So the main science objective here is to address the question, does the hierarchical nature of dark matter extend down to very low stellar mass systems going well below 10 to the 7th solar masses? Here on the right, you see a plot of the predicted number density of dark matter halos for different dark matter models. The cold dark matter one is shown in black, and then various variations of a warm dark matter model at different dark matter masses shown in the legend there, with the more massive warm dark matter particles being more abundant at low mass than the lesser mass warm dark matter models. But if you have, the key here is you need sufficient angular resolution and sensitivity to be able to find such halos in the universe. And so the goals of this are to A, get a census of the dark matter objects that are out there, and then convert that census to actually a constraint on the dark matter halo mass function, and even on the ultimately the mass of the dark matter particle. Why is this interesting? Well, in theory, we should be able to, with Habitable Worlds, detect thousands of such halos and resolve their internal structure using the strong lensing constraints. This would allow us to measure both the concentration and slope of their mass profiles, and potentially provide new constraints on the nature of dark matter. And then also doing this at different redshifts will further provide a very clear picture of how the structure of the cosmos forms and evolves over time. So here's the physical parameters that we're hoping to measure, is to measure the space density and mass function of these galaxy halos. And the number of targets determines the accuracy of the constraints on the warm dark matter mass estimate that we can make. And here, the people in this sub-working group have done a simulation to show the number of detections of such low mass halos that would be found in a survey of 1,000 lenses for different angular resolutions. And so the red histogram shows roughly a 30 milliarc second angular resolution, which is typical of what James Webb Space Telescope can currently do at about 1 micron. And you can see it can get barely down to about 10 to the 8th, but below that you would not find anything. You would not be able to resolve those subhalos accurately enough. But once you can lower, or I should say improve the angular resolution by at least a factor of 3, getting down to 10 milliarc seconds, which Habitable Worlds 8-meter telescope would be able to do at about 4,000 angstroms, the number of detections goes up dramatically by, in this case, you can see by almost 2 orders of magnitude. And going even further, improving the angular resolution improves things noticeably, but you get a really big jump once you get to at least 10 milliarc seconds. And so that's the sort of key driver on the observatory performance that this science case is going to require. So here's what the goal would be, is to do a survey of several thousand, well, several hundred, but maybe as many as several thousand such systems, as they showed that nice example earlier. And we would take basically a single image with Habitable Worlds and target known systems. And by the time Habitable Worlds flies, there are expected to be hundreds of thousands of such of these galaxy lens candidates, both from Euclid and the Roman Space Telescope survey. So the source with which to draw upon for this survey will be abundant. But those observatories, both Roman and Euclid, would not have the angular resolution to do the follow-up characterization of these subhalos that we would need. And if we had even only 100 systems with kind of the best conceivable resolution Habitable Worlds might achieve, we would be able to definitely measure the mass function, subhalo mass function, for warm dark matter, if warm dark matter had masses as small as 6 keV. Currently, there's only upper limits on the mass of the warm dark matter particle from existing observations. And so this is going to be a really revolutionary science case for Habitable Worlds. Okay, I'm going to move on to our next science case, which is probing the multi-scale and multi-phase circumgalactic medium with Habitable Worlds Observatory. And I think what you'll see here in this science case is, in the previous case, we were pushing the angular resolution capabilities of the telescope. In this case, we're going to be pushing the ultraviolet sensitivity of the telescope. And so this is a case being led by Joe, Sanch, Rangman, and Deborah, and they've done a really nice job here. And so what is this about? Well, this is to characterize the properties of the CGM. And the CGM, we now believe, is inherently multi-scale and multi-phase. And by that means, multi-scale means there's structure on scales going all the way down to even the parsec scale, all the way up to 1 megaparsecs. And this is due to a variety of physical processes within the CGM: galactic winds, thermal instabilities, turbulent mixing from radiative transfer. And then the CGM is also inherently multi-phase, meaning the gas is not all at a single temperature. The temperatures may range from 10 to the 4 to as hot as 10 to the 7 Kelvin. And there may also be coherent flows within this gas. And so what you're seeing on the right is a simulation of what this gas may look like, but we've never actually made such detailed maps of the CGM around any given galaxy. And so one of the goals of this science case is to show how we might begin to be able to test these models directly with observations. And the way we would do this is to rely on key spectral lines in the ultraviolet. So this plot on the right in the lower left shows a really beautiful plot that was made in part by the participants on the LUVOIR STDT. And it shows the tracers in the UV that can trace various parts of temperature and density parameter space of galactic gas. So highly ionized lines like magnesium-10, neon-8, oxygen-6 probe the highest temperatures and lowest density regions, and then carbon-4 and carbon-3 and carbon-2 and magnesium-2 can probe lower temperatures but higher density regions. And all of these lines are lines that have rest frame emission wavelengths in the UV, typically between 1,000 and 3,000 angstroms. And so currently, we are somewhat limited in what we can do with HST costs because it has no throughput below about 1150 angstroms. And also, you need to go to high redshift to access oxygen-6 and even higher redshift to access neon-8. So the goal would be to see what we can do to improve this situation with habitable worlds. So in addition to having this sensitivity all the way down to at least 1,000 angstroms or maybe even a little below, you also want high spectral resolution. And here is a sample of some of the high ionization spectral features that you would want to observe. And here you see two examples. You can barely see the underlying black line in the plot on the left, which shows the prediction for a spectrograph with a resolution of 100,000. You can begin to see some of it differences at 50,000. And then if we go to lower resolution here, about 30,000 on the left and 20,000 on the right. And 20,000, by the way, is the best resolution that can be provided by COS. And you can see even though you might think 20,000 is high, at this resolution, you lose a lot of the kinematic information in these spectral features because the lines become very badly blended. So you really want to have spectral resolutions of at least 50,000 to be able to do this problem well. So the goals of this would be to measure the column densities of various of these ionization lines down to very low column densities. And the goal is to constrain the temperature, density, metallicity of the sort of cold to warm gas. And to resolve the individual components of this gas down to a couple of kilometers per second and down to spatial scales of a few parsecs. So the way we would do this is by finding foreground galaxies that are in front of distant quasars and use the quasar absorption line, use the quasar as sort of a background light source to detect the absorption lines from the gas in the foreground galaxy. Now, with COS, we've pretty much only been able to use one quasar per galaxy because it's simply not, Hubble's simply not sensitive enough to go to very faint quasars. But with habitable worlds, we would be able to certainly observe the brightest quasars out there, but we would also be able to potentially use galaxies as a background source beacons, which would allow us to get down to far UV magnitudes as low as 20th or maybe even a little fainter. 90% of the Hubble spectra have FUV magnitudes that are brighter than 18th. But a habitable worlds could achieve even greater signal to noise for much fainter quasars at much higher spectral resolutions in just a couple, 2 to 3 hours. And this would allow us to go much fainter and get many more background sources per galaxy. And by doing multiple background sources per galaxy, in some cases up to 10 or 20 background sources per galaxy, we'd really be able to map out the CGM in great detail. We would also, by the fact that we could do this with high sensitivity in the far UV, focus on the lowest redshifts. And the advantage of that is that these galaxies subtend larger angular areas and potentially brighter targets. We also have the ability to combine the habitable worlds observations with facilities at other wavelengths in the X-rays and radio, and also from large ground-based telescopes. Excuse me. And so the goal is to eventually observe 100 sight lines with impact parameters of less than 50 kiloparsecs. And the goal here is by doing that, you'd achieve a source density of less than 10 kiloparsec separation, which is needed to really map out inhomogeneities in the gas flows in the CGM. So here are some of the constraints on the instrument performance that we would want for habitable worlds, and we've asked our researchers to try to say, where are we at now? What would involve what kind of instrument would enable incremental progress versus major breakthroughs? And you can see that the really major breakthroughs come when you begin to reach spectral resolutions of 50,000 or greater and have sensitivities that go down to at least down to 1,000 and maybe a little below 1,000 angstroms. And with that, we would then really be able to study the CGM around low redshift star-forming galaxies in the sort of M-star range. And so this is a really exciting project, and I think I'm now going to turn it over to Swara, who's going to talk to you about the last two science cases.
Thank you, Mark. So the next science case we want to talk about is regarding the ionizing photon luminosity function from star-forming galaxies. Next slide. So we know that reionization is a really important epoch in cosmic history. And in order to really understand reionization, we need to know what the ionizing photon budget is that is provided by star-forming galaxies, AGNs, and we also need to know what fraction of the radiation is able to escape from these galaxies. But the problem with understanding these parameters at high redshifts in the reionization epoch is that we're looking at a phase transition from a universe that's predominantly neutral hydrogen to ionized hydrogen. And most of the ionizing radiation is being absorbed by the neutral hydrogen. So we really are not able to directly measure or directly observe the ionizing continuum leakage from galaxies. But we know that they have profound implications. And even beyond, even after the universe is fully ionized, even at low redshifts, redshift 5, 4, 3, and below, you still have ionizing photon production by a large number of star-forming galaxies and AGNs, and they contribute to the intergalactic ionizing background. And that, again, has implications for structure formation. So our real hope of understanding the process of how ionizing radiation escapes galaxies and how much ionizing radiation is available and can leak from star-forming galaxies across a range of properties, that can only be done at lower redshift. So what this science case tries to do is understand the luminosity function of galaxies in the hydrogen ionizing continuum at the Lyman edge all the way across cosmic time from redshift 1 to the local universe. And we also want to understand what is the shape of the ionizing continuum at rest wavelengths below 912 angstrom, because that gives you a handle on the extreme UV emission, the integrated extreme UV emission from the star-forming galaxies. Next slide. So as I said, here the idea is to be able to directly detect the ionizing radiation, but we want to do that from a statistically large sample of star-forming galaxies that represents a range in the properties of star-forming galaxies. Currently, we are only able to do this for a handful of galaxies in the local universe, and those are picked by certain selection criteria. So they're not really representative of the star-forming galaxies across different properties and across parameter space. And we want to do this at low redshift where the IGM is relatively transparent. So the program is planning to look at star-forming galaxies all the way out to a redshift of 1.2. Next slide. So it's really an industrial search for Lyman continuum leakers, and so in the figure here, you can actually see what is the areal density of far UV emitting galaxies. So using the luminosity functions that are derived using Galax and VMOS data. We have luminosity functions for galaxies from the local universe all the way to redshift 1.2. So this figure shows what is the expected number density of star-forming galaxies per square degree per magnitude bin. And the two takeaway points from this figure is you can see how the median galaxy brightness moves to fainter magnitudes. So you want the kind of sensitivity that the Habitable Worlds Observatory can provide to be able to sample the far UV radiation from the star-forming galaxies at high redshift. And also, it gives you an idea of the number of such galaxies that are available for the study. So you can see that there are about hundreds of thousands of galaxies that are available within, if you assume a 2x2 arc-minute FO field of view for the multi-object spectrograph, then you can actually get samples of hundreds of galaxies in these different magnitude and redshift bins. Next slide. So the properties that we want to determine are is the luminosity of the ionizing photon continuum below the Lyman break, and also understand the escape fraction of ionizing photons, because we really want to understand how much of the ionizing photons that are produced are able to leak out of these galaxies and contribute to the ionizing background. And the method that will be used is low-resolution spectroscopy over a statistically significant sample of star-forming galaxies. So you're sampling over many properties of masses, ages, dust attenuation, and so on. Next slide. And here is a table that actually shows the state of the art and what is required to make major progress in this field. So first of all, the number of galaxies. Currently, all of the Lyman continuum leaker measurements that we have are using HST COS, and there are only a handful of galaxies that have been observed. I mean, of the order of a few tens, really, but less than 100 determinations. And all of those are at redshifts less than, up to around redshift of 0.3. And what we really want to do is have large samples of galaxies, and you can get large samples of galaxies with a wider area, and that's really where the Habitable Worlds Observatory becomes really, really the best way to do this and can ensure a breakthrough. Substantial progress from Roman and also the Explorer mission UVEX, which will give us enough targets to select to create the luminosity functions, but the issue is that we will be able to identify potential candidates that are Lyman continuum leakers, but we will not have the sensitivity to actually measure the Lyman continuum emission from those galaxies. And with HWO, the idea is we'll be able to sample at least 500 objects per redshift bin out to a redshift of 1.2. of a redshift bin of 0.2 all the way out to 1.2. And another thing is also the flux limits that we want to reach are at least 30-second AB magnitude, and again that requires a 6-meter or 8-meter class telescope. Next slide. So the observation, again, it's multi-object spectroscopy with a spectral resolution of 1000 and high spatial resolution. The high spatial resolution is needed because you really want to locate the continuum source, the UV continuum source inside the bubble or from wherever it's escaping. So you really need to focus on, you have to be able to put slits on the UV continuum source itself. And also, you're looking at rest frame wavelengths of 500 to 912 angstroms. So for the redshift range that we're talking here, that would be about 1,000 to 1,800 angstroms. And again, the most important thing about why we need HWO is the high effective area and the ability to go to 30-second magnitude, so high sensitivity and spectral resolution. Next slide. So here is a figure that actually shows the cumulative number of Lyman continuum leakers that you can get with signal to noise greater than 5 in 10 hours. And this is sampling across a range of escape fractions, going all the way from a few percent all the way to 100% escape fraction. And the important thing to notice here is that for each of these redshifts, you can see that you can get about few hundreds of galaxies can be sampled across the redshift bins, and the sensitivity that we can go all the way down to about 30th magnitude, and that's very crucial to be able to kind of sample the entire range of escape fractions. Next slide. And again, this is another slide that shows the total number of galaxies that you can get with escape fractions less than 10%. Sampled all the way up to less than 10%, and in about 100 hours, in about 100 hours, you're able to kind of get numbers like a few hundred star-forming galaxies at these different redshifts. And this shows for both LUVOIR A configuration and LUVOIR B. So in the case of HWO, we would be looking more at the green histogram, which is essentially LUVOIR B. Next slide. So here is a description of observations, and the state of the art right now is suborbital rockets and incremental progress with small sats, but you can see the substantial progress as the effective area is increased, and with the number of objects that you can sample in one pointing, with the number of shutters and the effective area that you have on HWO. And also the capability needed is to go down to about 912 to 1800 angstroms, so really going into the real far UV here. And the area covered is about 15 fields with 3 times 2 arcminute square field. And again, the idea is to have really good sensitivity in the UV to be able to go down to about 34th AB magnitude. Next slide. Okay, so again, I just want to say that the previous science case, of course, the ionizing photons, that's really key science that can only be done with HWO. And, so that's going to be one of the really defining science cases in terms of the short wavelength cutoff and the kind of sensitivities we want to reach. So I'm going to move on to the next science case, which is on AGN. This is done by our AGN working group. And here the idea is to be able to use the sensitivity and the high resolution of HWO to actually image the dusty torus and jets around supermassive black holes. Next slide. So a lot of the AGN science cases have this overarching goal of trying to understand the formation of supermassive black holes and how their growth is coupled to the evolution of their host galaxies. And we have a number of science cases that are looking at different science cases within this broad umbrella, but here we're going to focus on the one that looks at the structure of the dusty torus. So to try and understand how does the structure of the torus, the thickness of the dusty torus, affect the coevolution of black holes and their host galaxies, and also try to understand whether the thickness of the torus can reproduce the observed population of type 1 and type 2 AGNs, because the key structure that really distinguishes between a type 1 and type 2 AGN is the obscuration caused by the dusty torus. So the thickness of the dusty torus has implications for the senses of type 1 and type 2 AGNs. Next slide. So, so here is the conventional picture that we have for AGNs. You have the central black hole, surrounding which you have this really hot accretion disk, which is a source of intense UV and optical radiation. But it's often hidden from view because of this very thick dusty torus that is located around it. And this has been a way to explain the different types of AGN that we find, because they can be explained by the inclination of the dusty torus, which sometimes when it's edge on, it prohibits our view of the broadline region clouds and the accretion disk. But when you see it face on, you're able to see the emission from the broadline clouds and the accretion disk. However, the actual morphology of the torus, whether it's a clumpy torus or what's the thickness of the torus, this has been debated for decades. And it's really a very small parsec scale structure, and it's too small to be resolved even in the nearest galaxies. And it does have a lot of implications. Like I said, it affects the senses of or the demographics of AGNs that we try to measure across cosmic time, because whether you see an AGN or not depends on the ability of the torus to hide the accretion activity. And we are basing our identification of AGNs on the emission from the accretion disk and the broadline clouds. And again, if the torus is thick enough, it can shield the host galaxy from the intense radiation from the accretion disk, and that has implications on how the AGN affects the host galaxy. Next slide. So the science approach here is, it's a really interesting case where you're trying to determine the structure of the dusty torus through direct imaging, and you're trying to measure the thickness and the clumpiness of the dust disk through direct imaging, and seeing the shadow of the dusty torus as a silhouette against the background light from the host galaxy. And an example of this idea is actually shown here in the figure. The figure actually shows a dust disk around a young star. And the idea is in the UV is where the dust obscuration is going to be it peaks in the dust obscuration would be the highest in the UV. So you need UV wavelengths to actually measure the thickness of the dusty torus. So the program would involve multi-wavelength imaging, and also the multi-wavelength imaging to understand how the light is transmitted from the accretion disk towards the observer. And that would help us understand the dust grain properties, and the spectra would help to understand the chemical composition of the dust grains. Next slide. So here is the kind of improvement we are expecting. So the kind of angular resolution that you can get right now is of the order of 150 milliarcseconds from HST. And here is an example that shows an active galaxy Markarian 348, which shows these ionization cones in the HST WFPIC2 image, which suggests a nearly edge-on view of the accretion disk. And this galaxy is located at around 65 megaparsecs. So the targets for this science case are going to be galaxies that are less than 65 megaparsecs, where you can actually get the kind of resolution you need to observe the structure of the torus. And the model predictions for the dimension of the torus is of the order of few tens to about 100 parsec, and the kind of angular resolution you need to image them are of the order of few milliarcseconds. And so that's the major breakthrough, would require something like 25 milliarcseconds. And the wavelength coverage here, we're focusing more on the UV because that's where the obscuration is going to be the maximum and would give you the full extent of the obscuring dusty torus. Next slide. And here is another science case, which again is related to extraction of energy from the supermassive black hole to understand how the jets are launched, the energetic jets are launched from the supermassive black hole. So this is really an interesting science case where we're trying to ask very specific questions here, really trying to rule out one model versus the other, or try to see whether the jets are actually driven by accretion disk activity, or is it driven by the black hole spin. And another question is, what is the dominant jet collimation mechanism? Is it the wind pressure or the magnetic field? And here is a really good illustration of the multi-wavelength image from M87, which shows that you can actually see these jet features at different wavelengths. You can see it in the soft X-rays in Chandra, and the HST images very clearly show you the jet structure. You can see these different clumps, and what you really want to do for this science is to be able to get the kinematics across the jet. And HWO would have would have to have the kind of sensitivities to measure the kinematics of the clumps along these jets. And the key observables here are line of sight velocities of along the radial extent of the jet, understand the electron temperature and density from the nebular emission, and also magnetic fields. So this science case also kind of pushes for a capability of measuring polarization. So that's another. Next slide. And again, the key thing here is that with any of the current facilities, we don't have the spatial resolution required to resolve the structures along the jet. And the requirement here is about for a major breakthrough to be able to actually answer these questions about the launch of the jet, the energetics, and the collimation. You really need something like 12 milliarcsecond resolution. And also you want to sample the entire range of radio properties. You don't want to just look at the radio loud sources or just the radio quiet sources, but you want a large sample of radio loud and radio quiet AGN to understand this phenomenon, and also sample a range of accretion rates. So again, this is a very key science case that you can only do with HWO because that's the kind of spatial resolution and sensitivities that you require in the UV and optical. Okay, so with that, I will hand it over to Mark to wrap up the seminar.
Yeah, so what you've heard here is just, I want to just emphasize, is just a subset of the science cases. I hope you get a sense that people have really, gone fairly deep into some of these calculations. They're actually doing simulations and really trying to see what a telescope like Habitable Worlds Observatory, what I like to call, as Aaron indicated, a super Hubble. I want to, of course, thank everyone in the community who has helped with this, all of our co-chairs who are leading this subgroup, my colleague Swara, of course, and encourage you all to continue to think of driving science cases and exciting science to do, even though our goals are to wrap up this exercise by the end of the year. It doesn't mean that that's where it ends. Inputs and engagement will continue to be important especially in the next 2 to 3 years, where these parameters on the observatory and instruments will really be defined. And you'll be hearing a lot about the iterations and interactions between the astronomy community and the engineering technology experts and engineers who will be working together over the coming years. And finally, just let me say, it's not too late to get involved. If you have not yet been involved and are interested in getting involved or hearing what we're up to, just reach out to Swara and myself. We can help provide information on how to get more involved. You can also Google habitableworldsobservatory.org. I think that's the new NASA website that is up and running and can give you lots of information. So with that, thank you.
Thank you, Mark and Swara, for the great seminar. It summarizes really the hard work from everyone in the working group of what can be achieved in just a year. So if you go back to last year's seminar, we had a overview of HabWorld, of the instrument, of the telescope, given by Jason Tomlinson. If you revisit that, you can get more idea of what the hardware would be like. But I'm sure a lot has changed in the past year. But really this year in the science working group is about developing the science case to support why we need a 6 to 8 meter telescope. And of course, we have a long way to go before we will put this in the sky. So thanks for the seminar again. Let's open the floor for question. And of course, I will include a link to the new HW website, and of course, you can, in the recording and in a subsequent message out to the community. And of course, you can always reach out to Mark and Swara if you have any, would like to get involved. So Peter.
Yeah, and I see some of our science working group co-chairs have joined the meeting. So greetings to you all. Peter, I see your hand is up.
Yeah, thank you both this is a really exciting project and really wonderful presentation. Lots of fun to see what science is going to come. I was curious in general just to see if your working group teams have considered what science might be done from the ground and whether this science would be differentiated from what we might anticipate from the ELTs that we expect to come online in the next 2 decades.
Yeah, in fact, there's a whole separate science working group dedicated to just that question: is what is the landscape going to be like in the next decade or so from the ELTs and from the advanced from the SKA and other advanced ground-based facilities. So there absolutely is a lot of discussion going on because, and I'm a big advocate of this too, it's fine to think about the synergies between the two, but we don't want to, focus on science cases for HabWorlds that actually will be done by an ELT, 5 years before HabWorlds launches. So this is a very much a topic that's at the fore of the discussions going on.
Yeah, I just want to echo that and say here we have been really trying to focus on the driving science cases for HW in particular. So we've been kind of trying to see which ones cannot be done with the ELT, because those would be the driving cases for, but synergies, of course, that opens up an entire new area for science cases.
So of all the science cases you presented today, would you say that none of them can be, done by an ELT from the ground?
I think it would be, I think certainly the CGM case, you really need those UV lines, and obviously that is not something you can do from the ground. I think in Swara's case too, you're looking at shorter wavelengths, which are, even in the best scenario of what adaptive optics or multi-conjugate AO will allow from ELTs, it really pushes credibility to assume they're going to do much below, 8,000 angstroms in terms of diffraction limited performance. It'll be interesting to see what can be done on the dark sector one, where the main driver there is high angular resolution. And certainly that one is one I want to take a closer look at to see, what the competition from the ground might be.
Well, thanks again. This is very exciting work.
Chris?
Hi, thanks. So this is a question really directed over to Swara, I think. So I love that last science case that you presented about the jets, and I think that was produced by Meinek Singer over at Goddard. And you mentioned about polarimetry there. I just wanted to handshake about polarimetry and what you think the chances are for a first-gen instrument with polarimetry, or maybe even as we're thinking about servicing for Hab Worlds Observatory, where we could go with even next-gen instrumentation. Thanks, Swara.
Yes, so of course, as a first-gen instrument, whether we would have polarimetry, that is still yet to be decided. I mean, that's one of the reasons why we are having these science cases to show how important it is. So it's a little too early to answer whether it would be a first-gen instrument, but a future capability, of course, one of the idea is that the Habitable Worlds Observatory will be serviceable. So from that respect, there is probably a good chance that we could have that in future. So definitely, I mean, this is the time to advocate for that facility. And so I think this is a really good science case that brings that need into the highlight.
Awesome, will do. I'll continue to advocate, and I see Meinek online as well. So great, thank you.
Thank you for the question, Chris. Anyone else from the audience? Any other questions? All right. Okay, well, maybe some of them will reach out to you, Swara and Mark. So we're coming to the top of the hour. Let me just quickly say that in 2 weeks, we have a special seminar by Mia Povil from University of Maryland. And that's our first Fearless We Go slot. So just to repeat, we have seminars filled for all the first Wednesday of the month through the end of the academic year, and then all the third Wednesday of the month are what we call Feel As We Go. So if there are timely results or a talk that you would like to give, feel free to reach out to me or Benny Hawada, and then we can figure out where to put your talk. All right, so thank you everyone for joining us. The talk will be made available on YouTube afterward, and always check back for new talks. All right, thank you. I'll see you folks in 2 weeks. Bye-bye.
Take care.
Bye.